In this video, I'd like to talk about the math question of the day for Sunday, July 9th, 2023. And with this problem, we have this indefinite integral, and more complicated integrals like this one here are typically seen in a Calculus 2 class. So at this point, go ahead and pause the video, see if you can work through this on your own. And when you're ready, unpause the video and we can go through this together. Now, assuming that you have attempted the problem, let's start working through this. And you could start by trying to do some type of u substitution, but in order for that to work, you need a function and its derivative. And you almost get the derivative to t to the third power, since that's 3t squared, but because it has this -4, and it is all raised to this 5/2 power, that substitution won't work. But what we can see is that we have this quadratic term and we're subtracting a constant. And from there, that's a clue that we could try to use a trig substitution, since this is similar to one of the Pythagorean identities. The identity 1 plus the tangent squared of theta is equal to the secant squared of theta. If we rewrite this as the tangent squared of theta is the secant squared of theta minus 1, this right here is similar to this right here, but we can manipulate it so that we do end up with this identity, which we can replace with the tangent squared of our angle. So in order to do that, we need to set t equal to the secant of, let's say, theta, but it has to be multiplied by a constant. And we're going to square t. So we'll end up with the secant squared, but we want it to be 4 secant squared theta when we square this out, and we want the 3 to cancel out. And that way we're subtracting 4 from this, we can factor a 4 out, and we end up with our identity here. So we need to think, how can we get a 4 out front when we square this and multiply it by 3? And to do that, well, we can start by multiplying it by 2. That will give us 4 secant squared theta when we square it. But we also need to divide by the square root of 3. Since when we square this denominator, we'll get back 3 in the denominator, and that will cancel out with this 3 here. So we can test this. T squared then, if we square this out, we get 4 secant squared theta over 3. And you can see the 3's will cancel, and we get 4 secant squared theta minus 4, where we can then factor the 4 out, and we get back our identity here, which we can substitute for the tangent squared of theta, and hopefully that will simplify everything. But if we're substituting for t, we also need dt. So we need the derivative of this function here. The constant just carries along. And the derivative of the secant of theta is just the secant theta multiplied by the tangent of theta, and all of this multiplied by d theta. So we can make that substitution now. So let's plug in what we now know with our new substitution here. Let me just make a bit more room. So this integral becomes the integral of t to the third. So we have this expression here to the third, which would be 8, since 2 to the third is 8. And we have the the square root of 3 to the third, which would be 3 root 3. Root 3 times by root 3 is 3, and then we have another root 3 multiplied. And we have the secant cubed of theta. And then on this inner part right here, we have 3 multiplied by t squared, which we know is 4 secant squared theta over 3. And we're subtracting 4 from everything. And then we have dt, which is this term right here. So we get 2 over the square root of 3 multiplied by the secant of theta multiplied by the tangent of theta. And we are now integrating with respect to theta. So it looks complicated, but things should simplify. And by the way, this expression here in parentheses is raised to the 5/2 power. We don't want to lose that exponent there. So let's move down here and we can keep working on this integral. So let's now make some simplifications. We can factor out these constants. 8 times 2 is 16, and 3 root 3 multiplied by another root 3. Well, root 3 times root 3 is 3, and 3 times 3 is 9. So we get 16 over 9 on the outside. And we have a secant cubed theta, but we also have another secant of theta here, so that's secant to the 4th of theta. And this inner term here, notice the 3's cancel. We get 4 secant squared theta minus 4. Well, we can factor a 4 out on the inside, so that we get secant squared of theta minus 1. And we know this is just equal to the tangent squared of theta. So let's just rewrite that so that we don't have to rewrite the whole integral. We have the tangent squared of theta there. And all of this is raised to the 5/2 power. Then we still have a tangent theta on the outside from that differential, and we're integrating with respect to theta. And we can make a simplification here. Since we have a product, both of these will be raised to the 5/2 power. And for the 4, we can take the square root first. So that's 2 raised to the 5th power, which is 32. And since the tangent of theta is raised to the 2nd power, and we're raising that to the 5/2 power, we multiply the exponents. 2 times 5 is 10, divided by 2. 10 over 2 is 5. So the 2's cancel each other out, and we get tangent of theta to the 5th power. So that simplifies this in parentheses, and then we'll multiply that by tangent of theta. So we'll get it to the 6th power, and we can factor out this 32. We actually have 2 to the 4th multiplied by 2 to the 5th. So if we want, we could write that as 2 to the 9th over 9. We have this integral of the secant theta to the 4th power multiplied by the tangent of theta to the 6th power, and we have d theta. Now from here, let me just make a little bit of room so that we can keep working. We have this secant of theta to the 4th power, where this is really secant squared of theta times by secant squared of theta. And we know the secant squared of theta is just the tangent squared of theta plus 1. And if we make this substitution, we can simplify our integral and use a u substitution. Now 2 to the 9th, that is just 512 over 9. Then we'll substitute just for one of these secant squared. So we have secant squared of theta times by secant squared of theta, and we'll replace, let's say, the first one with the tangent squared of theta plus 1. And I'll rewrite the tangent of theta to the 6th next, and then all of this is multiplied by the secant squared of theta, d theta. So I just replaced one of these secant squared theta, which are multiplied together and form the secant to the 4th of theta. I just replaced one with this Pythagorean identity here. And the reason I did that is because now we can use a u substitution. And we can use the fact that the derivative of the tangent is the secant squared of theta. So let's set u equal to the tangent of theta. And we know du is the secant squared of theta, d theta. So we can make a nice substitution now. We have this is 512 over 9 multiplied by the integral. We have u squared plus 1 multiplied by u to the 6th. And the secant squared theta d theta is nicely simplified to just du. And this integral is fairly straightforward. We can just distribute the u to the 6th. We still have that constant on the outside, 512 over 9. But now our integral is u to the 8th plus u to the 6th. And we're integrating with respect to u. So let's keep working down here. And when we actually evaluate this integral, we get 512 over 9 multiplied by u to the 9th over 9. We're using the power rule for antiderivatives, plus u to the 7th over 7, and we do have our constant of integration on the outside. But we want to put this back in terms of theta so that we can then put it back in terms of our original variable. So we know that u was the tangent of theta. So let's start by putting it back in terms of u here. So we have, let me rewrite that, we have 512 divided by 9 multiplied by the tangent of theta to the 9th power over 9 plus the tangent of theta to the 7th power over 7, and we're adding our constant of integration at the end, and we need to go back to our original variable, which remember was that variable t, and we set t equal to twice the secant of theta over the square root of 3. So we need to relate theta to t now. And to do that, we'll need to make a right triangle. So let's first solve for the secant of theta. We have secant theta is root 3 multiplied by t over 2. And we can draw in a right triangle here. And remember that secant is related to the cosine function. And since cosine is adjacent over hypotenuse, secant would be the hypotenuse over the adjacent. And let's say this is our angle theta right here. So the hypotenuse is this root 3 multiplied by t, and the adjacent is 2. And we need this opposite side, which let's just call it x. We can use the Pythagorean theorem to relate these. We have 2 squared plus x squared, or 4 plus x squared. This is equal to the hypotenuse squared, which is 3t squared. And solving for x squared is 3t squared minus 4. Square rooting everything, we get x is the square root of 3t squared minus 4. So we can figure out the tangent of theta. That's just the opposite over the adjacent. The opposite was the square root of 3t squared minus 4 all over the adjacent, which is 2. So we have our information now. We can plug this in and rewrite what our integral is actually equal to. Let's do that down here. This is 512 divided by 9. We have the tangent of theta to the 9th power. So we have this expression raised to the 9th. It will get a little bit messy, but we have the square root of 3t squared minus 4 all over 2 raised to the 9th, and then all of this is divided by 9. Then we have plus this expression for the tangent of theta to the 7th. So square root 3t squared minus 4 over 2, all raised to the 7th, and then all divided by 7. And we still have our integration constant plus c on the outside here.